Here we'll look at the covalent chemical bond as a first type of bonding model that we'll examine, and we'll look at covalent bond energies and chemical reactions. Now keep in mind that a chemical bond is a force causing groups of atoms to behave as a unit, and this occurs because there's some stability in the group compared to the individual atoms. If we look at the methane molecule, for example, it requires 1,652 kilojoules of energy to break methane into elemental carbon and 4 hydrogen atoms. Or we can say that upon the formation of methane between carbon and 4 hydrogens, we release 1,652 kilojoules of energy per mole when this bonding occurs. Here we have 4 equivalent carbon-hydrogen bonds formed. If we divide 1,652 kilojoules per mole by 4, we get 413 kilojoules per mole, which is the energy of stabilization, or the energy released when a carbon-hydrogen bond forms. It's the bond energy for each carbon-hydrogen bond. Now, one thing to keep in mind as we're going through this discussion of covalent bonding is that models are attempts to explain how nature operates on the microscopic or atomic level based on experiences in the macroscopic world. A model does not equal reality. Models are oversimplifications and are therefore often wrong. Models become more complicated and are modified as time goes on and as more information comes to light. We must understand the underlying assumptions in a model so that we don't misuse that particular model. And when a model is wrong, we often learn much more than when it's right. Now, bonding models came about to explain why most atoms exist as collections of atoms and chemical reactions appear to simply involve rearrangements. Remember, bonds occur because collections of atoms have lower energy than individual atoms, and electron sharing lowers the energy of atoms. By knowing the fundamentals of bonding based on simple molecules, we can make accurate predictions of very complex molecules. Now, when we look at bond energies, we're looking at the energy associated with an individual chemical bond. To break bonds, energy must be added to the system. This is endothermic. The energy term here carries a positive sign. When bonds form, energy is released. When energy is released from our system, this is exothermic, and the energy term carries a negative sign. Here we have a collection of average bond energies for various chemical bonds between both homonuclear and heteronuclear species. Now we can have single bonds where we have one pair of electrons shared. We can also have double bonds where we have 2 pairs of electrons shared, or triple bonds where we have 3 pairs of electrons shared. Notice that we see an increase in bond energy for multiple bonds. If we compare a carbon-carbon single bond, it has a bond energy of 347 kilojoules per mole. To a carbon-carbon double bond, we have 614 kilojoules per mole, almost double. And a carbon-carbon triple bond is 839 kilojoules per mole. We see the same trend with oxygen, where an oxygen single bond is 146 kilojoules per mole for homonuclear oxygens. When we have an oxygen-oxygen double bond, we're looking at 495 kilojoules per mole. Now, when a chemical reaction occurs, we can calculate the change in enthalpy for that reaction by looking at the sum of the energies of the bonds breaking minus the sum of the energies of bonds forming. We can go ahead and predict the change in enthalpy for the following reaction given bond energy data. Keep in mind that this is simply the sum of the energy of the bonds breaking minus the sum of the energy of the bonds being formed. Here we have bonds breaking minus bonds forming to give an overall change in enthalpy for this reaction of minus 42 kilojoules. Now we can also look at bond length and bond energy. If we look at a carbon-carbon single bond, it has a bond length of 154 picometers and a bond energy of 347 kilojoules per mole. A carbon-carbon double bond is shorter than a carbon-carbon single bond. There are more electrons between those two nuclei. The nuclei are being held more tightly together with a bond length of 134 picometers. The bond energy is also greater at 614 kilojoules per mole. So in going from a bond order of 1 in the single bond to a bond order of 2 in the double bond, we've decreased our bond length. We have a stronger bond, as is indicated by our bond energy, which has gone up. When we go to the carbon-carbon triple bond, bond order of 3, we now have even shorter bond length of 120 picometers and a higher bond energy of 839 kilojoules. Again, as bond order increases, bond length decreases and bond energy increases. We see the same phenomena with the carbon-oxygen bond. The carbon-oxygen single bond is longer and weaker than the carbon-oxygen double bond. The same trend holds for the carbon-nitrogen bond. The single bond is longer and weaker than the double bond between carbon and nitrogen, which is longer and weaker than the triple bond.